So in this reaction, or excuse me, this lecture, we're going to be talking about a new reaction, which is the generation of, or the synthesis of acetals and ketals. This is a hugely important functional group present in organic chemistry. And the way we make these things is actually just from carbonyls and alcohols. So here's kind of the gist of the functional group. We have acetals and ketals are basically the same thing. Okay, so how this works is if we take a molecule like this, a carbonyl, and we add, I'm going to write 2 ROH present. That's okay. But in general, there's usually an excess much greater than 2. But just to balance the equation, all we need is 2. And what we're going to get as a product is we're first of all going to get water. This is a condensation reaction, and that's important to understand. And then we're going to use H plus as a catalyst to drive the formation of a ketal. Now, a ketal is a carbon with 2 oxygen atoms present at the same atom. So this is unusual. It's not like an ether. It's a carbon with 2 oxygens present as opposed to an oxygen with 2 carbons present. And on either of these oxygens, we're going to have that R group that was part of the alcohol. Now, here's where the nomenclature comes from, acetal and ketal. If we start with a ketone, then we get a ketal. Now, conversely, because it's such an important functional group, I guess, if we have an aldehyde, we get an acetal. So we're going to add that aldehyde now to an excess of alcohol. I'm just going to show it as 2 alcohols to balance the equation, but it's typically a bunch of alcohols. And we get now an acetal. You'll notice the difference between the acetal and the ketal is the starting material, and then in the product what happens is that carbon that I've highlighted with a dot, that carbon with the 2 oxygen atoms has either a carbon on both sides or a carbon on one side, hydrogen on the other side. Okay, so the way to kind of think about this reaction is to first of all get comfortable with the functional group. So recognizing an acetal or ketal involves finding the carbon with 2 C single bond O bonds. That is, we don't have a carbonyl now with this carbon. We don't have a carbon-oxygen double bond. Rather, we have 2 single bonds to oxygens. Okay, that's what makes the acetal and the ketal. And then if we have a hydrogen on one side or a carbon on the other side, that'll tell us whether or not we have an acetal or a ketal. So how does this reaction work? That is sort of the calm before the storm. How do we approach this before we think about the mechanism? How does the synthesis of either an acetal or a ketal, it's the same process, just different starting materials and very subtle differences then overall. How does the synthesis of the acetal or ketal work? So first of all, we have to recognize that this is an equilibrium process. So all steps are highly reversible. All steps are highly reversible. Additionally, all steps follow Le Chatelier's principle. Let's see. Le Chatelier. Somewhere in my notes is a spelling for Le Chatelier. Here we go. I don't know if this is right. It's just at least from my notes. Le Chatelier's principle says that in an equilibrium, adding a component to one side will increase concentrations or amounts formed of things on the other side. Okay, say it a different way. If we increase the starting material, the Chatelier's principle will then say we have to increase the product because an equilibrium has to exist. So if we wanted to increase the amount of product that was formed, we could just continuously dump in starting materials, and that would drive the equilibrium over to the right to increase the concentration of products. Now, similarly, if we take away product, we will then increase the amount of starting material and actually form more product. Okay, so there's a little bit of a subtlety in this latter point, because one of the products of many condensation reactions is water. And so what you can do is actually figure out ways to remove water, dry the process. And by removing water, you're removing product and causing the equilibrium to further produce more of our desired product and water as it tries to reestablish equilibrium. So if, let's say, at equilibrium, we only saw 50% of our stuff react, that is, if we at 100 moles of starting material, we reach equilibrium, there's 50 moles on one side and 50 moles on the other side of the chemical reaction equation. If we pull away water, I don't know which way you're seeing right and left right now, but if we pull away water from the product side of the reaction, actually greater than now greater than 50% of the starting material will be consumed as we try to offset that lost water and reestablish equilibrium. So it's a fun little trick to drive the reaction forward. Now, alternatively, we could just add one of the starting materials in huge excess to drive the reaction over to the product. So anyway, the Chatelier's principles at play here, all steps are reversible. So typically what we do is we add a bunch of ROH, a huge excess, I should say, an excess, an excess of ROH, and or simultaneously remove water. What we'll look at in future lectures is we can reverse the process of acetal and ketal formation by adding additional water to the reaction. Okay, now let's look at a mechanism for this. And the mechanism is going to be for a reaction where we have, in this case, acetone, and we'll react it with methanol, where the methanol is in excess. We have an H plus catalyst here. And that H plus catalyst is going to lead to the formation of this ketal, where we've got two MEO groups now attached to the carbonyl, where water is a byproduct. Okay, so first things first, this is the overall reactions. First things first, H plus catalyst react first. It's just a subatomic particle. I think we've talked about this, but we've taken a little break from talking about acid catalyzed reactions. Let's get back to it now. H plus catalysts react first. Now, how are we going to let that react? Well, the H plus is going to engage the carbonyl. Now, how do we think about how it's going to react with our carbonyl, which in this case is the ketone acetone? Well, let's go back to that resonance structure that's oh so helpful. Okay, we've been focused so much on letting the positive charge tell us what's going to happen. In this case, we're going to let the negative charge dictate things. It's going to be the negative charge in the carbonyl that tells us we're going to form an intermediate where the oxygen is now protonated and neutralized. But notice we came from a resonance structure with a positively charged carbon to do this, and we have to make sure to keep it that way as we do the reaction. Okay, so once we protonate the carbonyl and we get to this species which has a carbon with a positive charge, we can better see how our methanol or any other alcohol will engage. These things are weak nucleophiles, poor nucleophiles, excuse me. Poor is better, weak is for acids and bases. These things are poor nucleophiles, but in the presence of a full-blown carbocation, we'll see them engage the positive charge using a lone pair of electrons on the oxygen atom. I guess I can make that bigger. So the oxygen is going to attack the positive charge giving us the foundation now for our ketal carbon, which now has 2 oxygens single bonded to it. Coming along for the ride with this oxygen are the methyl group and an H atom. If you notice, after we add, the oxygen must be positively charged. So what we need to do at this point is neutralize that positive charge by losing an oxygen atom. When we do that, we get to a very useful intermediate structure, and we're halfway to our ketal product. This is called the hemi or half ketal, and it could be an acetal as well. So with a hemi ketal or acetal, we're 1/2 way through the mechanism. Now we'll see why it's important to call attention to this functional group as we look onward. Okay, so after the hydrogen falls off, we have an H plus floating around. The H plus is looking for somewhere to go. It could go to more starting material to activate other reactions, but we're still not done with this first reaction. We have 2 oxygen atoms with lone pairs present. We're actually going to choose the oxygen atom with it's an OH. Why did I choose that one? What is so special about it? It turns out not too much other than it sends us on our way to form the product. You could very well say, I don't like it, Willoughby. I want it to go on the methoxy oxygen. I would be like, okay, if you do, you're going backwards a step. If you look at that product on on the lower right part of your screen, you'll see that oxygen on the lower part with the methyl group has a hydrogen on it. That's what you would get if you put the hydrogen. You would just go backwards, and all of the steps are backwards. Remember, we're trying to drive the equilibrium forward using Le Chatelier's principle by either adding a huge excess of methanol or removing the water that we're ultimately going to lose from this reaction. So we are driving the reaction towards product, and we just need to figure out the best way to get there. And it turns out it has to be when that oxygen finally makes up its mind to pick off the H plus. When we do that, we get to a good leaving group. That is an H2O group present on our molecule. And recall, this is a condensation reaction. Like the reaction to form an imine, we have to figure out a way to drive water off. And we can do it here. We can let the oxygen leave, or we can let the lone pair of electrons from the OMe come down, whichever way we want to do it. And that would give rise to, I'm just going to flip these methyl groups up, a lot like our imine reaction. That would give rise to this structure if I show 2 arrows, or this structure if I show 1 arrow and I leave the positive charge in the carbon atom. Both of these structures are resonance structures, and they're both fine. Maybe the right one's your preferred method because it shows you what's going to happen next. So what we've done here is we've lost water. H2O floats away, and if we're actively removing it, we're driving the reaction forward. At this point, we're going to add some methanol to the reaction. Methanol is already added to the reaction. We're going to add methanol to our molecule. So the lone pair of electrons once again see a positive charge on carbon that will add to form this species here, which now has a carbon with 2 single bonds to oxygens. Now, both of those oxygens have methyl groups, so we're already there. All we have to do is lose this hydrogen atom to neutralize our structure, and we get a carbon with 2 OMe's and 2 methyl groups. This is our ketone. Now, what else was formed in this last step? We regenerated our H+, which is a catalyst. If you recall, a catalyst is something that's consumed and then regenerated. The H+ that we got out that's being used for subsequent reactions and will be present at the end of the reaction, all of those things are different. The one we start with, the one we finish with after one reaction, the one we finish with after a mole of reactions are all different hydrogen atoms that scramble with the solvent and go all over the place. There's no way we get the exact same one out. Okay, but it's still a catalyst. It's decreasing the barrier for the reaction by making a positively charged carbon that's more reactive with the methanol, and it's regenerated, so we don't need to add a stoichiometric amount of it. Okay, so there's the mechanism for formation of the ketal. What I want you to do is not worry so much if you're not getting this just from watching me do it. What I want you to do is practice this and see all the steps that are repetitive. Remember, the driving force is we need to lose water and get to product. Know what you're trying to get to. If you recall from mechanism problems, I'm not going to just hand you a blank slate. That is starting materials plus catalyst gives what, and give me a mechanism for it. Remember, I always give you the product and say, now propose the mechanism. Speaking of predict the products, let's go ahead and practice some predict the product questions. So predicting the product for acetals and ketals. And remember, I'm not too worried about the nomenclature acetals and ketals. They're both pretty much the same. But let's look at some examples of these. So let's say I'm just going to write a bunch of questions. So I take benzaldehyde plus an alcohol. I write an excess, and then I've got an H plus catalyst. And I'm going to use an H plus catalyst in every case that I'm not going to define. Got excess alcohol down here. We've got this one. Let's get another aldehyde in here. And then a little bit of an interesting one at the end here. Okay. So in every case, what I'm going to do is I'm going to redraw the carbonyl framework. And I'm going to have my carbonyl carbon attached. I'm going to draw this hydrogen on these two aldehydes because I feel like that makes things a little bit easier to see. But on every case, I'm going to redraw the carbonyls with two oxygen atoms present. Then I'm going to go back and figure out what's attached to those oxygens. Okay, so now I've got my two oxygens on a single carbon to form a ketal or an acetal. Now in this first case, I have an ethyl group from ethanol, so I could just draw that, or I could write ET. Okay, so that would be a correct structure. Probably you want to just stick with drawing the thing or writing ET, not a mix. Okay, now down here we have an isopropyl group, so I'm just going to write what I see on the alcohol, which was this group here. This next example is kind of wonky. We have H2O. Well, two of the hydrogens leave to help with the formation of water. So I guess the other hydrogens stay put. Okay, cool. All right, now this one we have methanol again. It's just on an aldehyde. Now this last example, what I want to highlight here, literally, is that our molecule of interest actually has two oxygens connected by a two-carbon bridge. So I could just draw that where the oxygens are connected by a two-carbon bridge. And we'll talk more about these in the next lecture, but this would be a cyclic ketal, which is pretty cool. Okay. What I want to do is finish with some important kind of concepts related, an important consequence of these reactions. You know what, though? Let's just keep it for another lecture. We'll stop here, let you guys kind of pause here, pause the video, write down the answers if you're not following along, and then we'll pick up with just a brief example of this before we move into practical applications of these. Yeah, next time. Okay, we'll see you then.